All right, so the reminder, I asked you to do the 4.1 AP classroom assignments. There's 2 videos in 4.1, so Unit 4, 4.1 is the topic. And the classroom videos, there's 2 that are pretty short, and then there's 6 multiple choice questions in the topic questions. So make sure you're getting that done by tonight. And then the other thing is we're going to start test corrections in class, and I just want to tell you they'll be due next Friday. So you have 1 week from today. We probably have 10, 15 minutes at the end of the period today to get started on it. And then we'll take probably 20 or 25 minutes on Monday also to work on it. So you'll have some time today and Monday. And then if that's not enough time in class, you'll have to finish the rest on your own before next Friday. All right, any questions about schedule? Okay, so today we're going to finish going over that second FRQ from 2019 and helping you understand why the answers are what they are. So hopefully you had a chance to pick up the papers in the back. If not, go ahead and grab them while I put the attendance in. All right. So for that FRQ, we've got the scenario of a block hanging over a pulley attached by a rope to another block that's sitting on a table, but the block on the table experiences no friction and the pulley experiences no friction, and both the string and the pulley are considered to have negligible mass. So you're basically only worried about the block's mass and for block B and block A, and then just correspondingly what that does to the tension in the string. So the first part says, suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of acceleration of the blocks once you release them. And then explain. So here's what they have as the solution. So you can follow along on that handout if you picked it up, the scoring guide. Some examples of answers that would be considered correct. You could say 0, you could say it's small, you could say it's negligible, you could say it's much less than G, or you could say it's less than G, which is just like the shorthand for saying much less than. I was very surprised looking at this rubric that they allowed 0, because it really isn't 0 unless they're so different. Like if it was, the mass of the Earth compared to the mass of an atom or something like that, but that's impractical for this scenario. So it could be very different, and it might be very, 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 very small, but to say 0 is surprising that they would account that. So, but they do. And now do notice that it says for a correct answer and attempt at consistent justification for 1 point. So if you gave the correct answer but you didn't justify, you don't get that point even though it was correct. And then the second point is if your reasoning or justification is correct. So it's worth 2 points possible total. And the only way you can get the first point is if you have the right answer and you tried to justify it. And the only way you can get the second point is if your justification was correct. And so they give a couple examples. Nearly 0 because block A is much heavier than block B. That will get you 1 point because the nearly 0 is fine. The block A is much heavier than block B. That's just restating the question. It's not really giving a clear rationale. And then the 2 point examples, very small, that's correct. Because block A has a large inertia, it won't speed up very much. So now you're connecting the fact that its mass indicates something about its inertia. And inertia is the resistance to acceleration. So if it has a large inertia, it would resist accelerating, which would basically stop the system from going fast. And then that second example, they said close to 0 because block B is so light it can hardly budge block A. I'm a little surprised that they allowed that for 2 points, because to me saying block A is just so much lighter that it can hardly budge, that's not a whole lot different than just stating the converse of the question, but they counted it. So That's the two examples that they gave. And then they give you kind of a claim evidence reasoning. If you like thinking through that format of answers, they kind of give you how you could phrase it that way. So any questions on part A, the first section? Does it make sense? All right. If we look at the second portion, now they're saying, suppose that mass A is much less than mass B. So now it's really tiny and mass B is really big. And same thing, giving an explanation. On this one, you would say that it's G or some number that's worth G. And I was again surprised that they didn't make you specify that it wouldn't be exactly G, but it would be nearly G. I would have thought they would have required that you said nearly G or almost G or slightly less than G, something like that. But if you just said G, they count it. And so here you can see it's only worth 1 point, and you have to get both the answer and the justification correct. If you miss either part, you don't get a half point. There's no partial credit. It's just 1 point or 0. And then they give a couple of examples. You could say it's nearly G because block B is almost in free fall. And you could say it's 10 meters per second squared, which is basically G, because block A has negligible mass and the string tension is nearly 0. And then they give you claim evidence reasoning process if you like that format. So, questions for part 2 of question A? Making sense? All right, I feel like that part A, it's a little less intuitive. I think sometimes students wouldn't probably think of that initially, but it's a good one to process because that is a style of question you might see. And I think it's also good for you to see how they word the rubrics and how they award the points. So you just get more and more comfortable. You can start to predict more and more what they might be asking for. All right, then question B. Now suppose that neither mass is much greater than the other, but they're not necessarily equal. Draw the free body diagrams, basically. Forces, not components, represent each force by a distinct arrow starting on, pointing away from the dot. So if you remember the video we watched where they specified all those things, you can see they use that wording on almost every question when they ask you to draw free body diagrams. And if we look at block A, it has normal force up, weight force down, and tension to the right. If we look at block E, it has weight force down, tension force up. That's all there is. And so you can see how the points are awarded here. You get 1 point if you labeled the normal force on block A correctly. So you could call it N, F sub N, normal force, force of the table, table force, or any other label that clearly indicates it's a normal force or that it comes from the table. So they're a little less picky on how you label it as long as it clearly indicates the table is supplying some sort of upward force. The second point says for gravitational forces on both diagrams. So you have to have it on both to earn this point. And you can just see they say you can use FG, F grav, W, MG, MAG, gravity, grav force. But you may not use just G, big G, or little g. If you did that, then you don't get the point. And also it says, and no extraneous forces on the diagram. So if you put some other force on there, you also lose this point. And that's pretty typical. In fact, when I was grading your tests from this last unit, that was the way the rubric was worded for one of the questions, that if you had extraneous forces, you would lose a point. And so for some of you, you had the forces correct on there, but then you added something that isn't supposed to be there. And so like you had a force that doesn't really exist. And so, or it doesn't exist in that scenario. And so you would lose credit for that. And they almost always have something in somewhere about no extraneous forces, no extra forces. And then the third point, for correct tension forces with the acceptable labels. So again, you have to have the tension force in both diagrams to get this point. And they said you can call it tension, string force, FT, F tension, F string, FS, T, or some other label indicating that the force comes from the string or from the tension. You cannot say it's MBG or FMB or something like that, because while it's caused by the weight of block B, that's not the actual force. The force is the tension in the rope. So it has to be something related to the tension in the string to count. So questions for part B. All right, you can see there's quite a bit of specificity in the rubric of what can count and what can't. All right, now move on to part C. Derive an equation for the acceleration of the blocks and after release in terms of MA, MB, and physical constants. So you always want to be careful about this phrase, in terms of. I also noticed when I was grading your test that there was one question where you had to do that, and a lot of students came up with an equation, but it wasn't with the correct terms. So you'd have to be careful about that. They give you two ways to solve it. One is using Newton's second law for each block, and then combining the equations with the correct notation, and then correctly using MA and MB since those are required terms, and then coming up with the correct equation. So 1 point for the correct equation, 1 point for using Newton's second law on each block, 1 point for using the correct terms. Okay, Ashley, have a question?
Would you have to factor G out?
No, I didn't on mine, and so that's fine, as long as it's mathematically equivalent. So I want to show you the math for this. But before I do, let's take a quick look at these free body diagrams to make sure we're clear. For block A, what is the net force?
The tension force.
The tension, because the normal and the weight cancel each other, right? It's not rising or falling. So for block A, the net force is the tension force. It's the only thing that doesn't cancel. For block B, what's the net force? Yeah, the weight minus the tension, because it's going to fall. There's no friction to keep it from falling, so it's going to fall. So the weight has to be larger than the tension. It won't be in free fall because there is tension, but it will fall. So gravity has to be more than tension. All right. So now let's switch it back to this. Have another. Let's just do it here. There's space here. I can squeeze it in. So, and I think it makes sense to have it right beside the picture. So for block A, we can say the net force is two things. It's MA, so the mass of object A times the acceleration it experiences, and it's also the tension force. Are we okay with that conclusion? Does that make sense? Okay. And then for object B, so we're looking at them separately initially. So for object B, the net force would be MB times A, 8 minus the tension. Are we okay with that one? Kind of looks like an O. Make sure that's clearly an A. Is that making sense there for object B? We're just looking at them one at a time. All right, so now you can see that both of them, we've got FT as part of an equation, so we could put them equal to each other. This one I'm going to rewrite just a little bit, though. I'm going to say FT equals, so put that over there, it'd be FG minus MB times A. Okay, so we're just isolating FT. We okay with that? Just doing that little algebra there. And now putting them together, I'll just do it over on this side. So we've got M of A times its acceleration is equal to FG, and let's just go ahead and change that to MB times G, right? This FG, let's make it M of B times G minus M of B times A. Any questions on that? Connecting the two equations, are we okay with that? All right, they want us to solve for A, so we need to get the A's on the same side. So mass of A times acceleration plus mass of B times acceleration times G. Okay there? All right, and then we can factor out the A. So A times the sum of mass A and mass B is equal to the weight of B, mass B times G. So then when we solve the A, we just divide. So A equals mass of B times G over mass of A plus mass of B. Okay, so that's the steps they're expecting, something along those lines. It wouldn't have to be exactly that, but it needs to be in terms of MA and MB and constants. So G is a constant, which is acceptable. So that's where they came up with the answer using the first sort of processing. Yeah.
I get water.
Any questions on the math there? Or conceptually? All right. So if we scroll back down to this part C, that's basically the math steps you would use for the way they answered it here. For the alternate solution, that's actually probably the way I would have thought through it. For whatever reason, my brain just tends to go that direction in problem solving for these kinds of problems. If yours doesn't, no worries, they'll both always work. You can take a purely sort of mathematical system of equations, or you can think about it as a whole system, which is just the way my brain works. So I would have thought it this way, that the net force of the whole system is the total mass times the acceleration that it experiences. Because both A and B have to accelerate at the same rate since they're connected. So whatever the acceleration is, it has to be the same. So that means the whole system has that acceleration. So the net force would just be all the mass times that acceleration. But the only thing that causes the net force is the weight of B. There's no friction, so only weight of B makes that net force. So the net force is the mass of B times G, and that equals the total mass, which is just MA plus MB times the acceleration. And then you just solve for acceleration. So it's a little bit shorter mathematically. They actually kind of show you the steps here. It's just those 3 steps. You don't have all the other things to go through. But I think for some students, it's maybe a little bit harder to see it as a whole system. I like it because I think to me it abbreviates it and it just clicks well with my brain, but it may not with your brain. So if your brain works better with the system of math equations, by all means use that. Use what works best for you. Thank you. Any questions on part C? All right. Part D says, consider the scenario from above where the mass of A is much less than the mass of B. Does the equation that you just came up with in part C agree with your reasoning? So if your reasoning was correct above, that it would basically just be acceleration due to gravity, then this equation supports it, because if we look at that equation there, the MA is in the denominator, and so if that's really small, it's not going to change the denominator much, which is going to make it end up being just the mass of B over the mass of B, basically. And so the acceleration would just be due to gravity. So in other words, A would equal G in terms of acceleration. Does that make sense on that? If A is so small that the denominator is basically just MB, MB divided by itself is 1, right? So A just becomes G. And now notice here on the rubric, it says correct answer is yes, no points. Note, no is acceptable if the equation is inconsistent with the answer in the above, in part A. And so if you missed part A, but got the equation right, then most likely they don't agree. And so if you said they don't agree and you explained it properly, you can still get this point even though you missed part A, okay? Or if you got part A right, but your derived equation was wrong, they probably won't agree. So if you said, no, they don't agree, and you explained correctly that they don't by the math of it, you would miss points for C because your derivation was wrong, but you could still earn D because you clearly explained that they weren't equivalent, that your answers didn't match. Okay? So you could miss one or the other and correctly explain that they don't match and earn this point for D. You would still lose the points above, but you would gain the points for D. Yeah, Griffin?
Shouldn't you try to match them though, like if you see they don't align?
I think that's probably wise, that if you see they don't align most of the time, now there's a few exceptions, but usually if they don't align, what they're usually giving you is they'll say some students performed an experiment and this is what they came up with. Does it support? So in that case, it could be yay or nay. But if you derived it, then ideally they should line up. So yeah, keep that in mind, that if they don't agree and you derived it, then probably you made a mistake either when you derived it or in the previous part. But if you can't figure out why, then just answer this and you'll probably still get the point, because this is pretty typical. They try to avoid double penalties as much as possible. It's not always possible, but they do try to avoid it. So any questions on part D? All right, actually I don't think it's gonna let me scroll. Oh, maybe here I can. All right, so here they're just giving you some examples and you can read those on your own. If you're watching the video, this is in Unit 2C. You can find this question and the scoring guide, or you can just Google it because it's available online. It's a released question. All right, for part E, while the blocks are accelerating, the tension in the vertical portion of the string is T1. Next, the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in this version, the tension in the vertical portion of the string is T2. How do the two tensions compare? So they're basically saying you used to have like a little fidget spinner that's so low friction that's basically you can ignore it. Now you've got like a water wheel, so you can't just spin it with your finger. Okay, it's going to take some force to get it to spin. Okay, that's basically what they're saying here is the scenario. And so the correct answer is the scenario with the pulley that is massive would create more tension in the string. So T2 would be larger than T1. And then your reasoning is where you're going to get one of the points. So ideally, you would come to the conclusion that the acceleration of both blocks would be smaller, because you still have block A and you still have block B, or block A and block B, however. But now you've also got the mass of this pulley you got to get spinning. So there's more mass, there's more inertia resisting the acceleration, because inertia and mass are kind of hand in hand. So if there's more mass, there's more inertia. It's harder to accelerate. So if the pulley now gets added in, it's going to be harder to accelerate, meaning the acceleration will be less. And so if the acceleration is less, the weight of B didn't change. And so if the acceleration is less, the tension up must be greater to make the net force less and make the acceleration less. So that's sort of the logic behind it. And then they give you a couple ways you could phrase it. And then they give you an example down here. I do want to mention this example down here because they use this term, which we haven't learned yet, so you wouldn't have to use this term, but that's a term we're going to learn in Unit 7. So I want you to see it now, kind of a foreshadowing. So they say the rotational inertia. You could have just called it inertia, but the rotational inertia, the second pulley, results in a smaller acceleration for the blocks. Block B must have a smaller net force to have a smaller acceleration. So the rope tension must be larger than before. In other words, closer to the weight of the block. So just want you to see that word. We haven't learned about rotational inertia, but conceptually it's the same as just regular inertia. The more mass it has, the harder it is to get to spin. But with rotational, there's another element that you also have to factor in. It doesn't apply to this question, but it applies to other scenarios we'll learn about in April. All right, questions? Anybody have anything you want to ask about the FRQ? All right, we'll keep practicing those as we continue throughout the semester, because you need more and more practice to get more and more prepared for May. We'll try to do about one a week. So we didn't get one last week, but we got one this week. We'll do at least one next week, hopefully. All right, so the rest of today, I'm going to do some notes. The first part is going to be all review. So I'm going to go through it pretty quickly. If I say something too quickly or go over something too quickly, just slow me down, ask questions. I don't want to leave anybody behind, but it's mostly review. Then we'll get into a little portion where it's some new scenarios. So we'll slow down a bit there. And then there's some more review that we'll kind of fly through a bit. And then we'll end with some more new scenarios. So kind of ebb and flow. But if I ever get going too fast, just slow me down. All right, so we've talked about energy quite a bit now, and I like this flow chart because it kind of helps you see that if we're thinking about the energy that we can calculate, it all falls into one of two categories. It's either kinetic because it's moving, or it's potential because it's not moving. Okay, or it could have a combination of the two. But if we're trying to calculate it, we're going to calculate it as either kinetic or potential. And there's different equations for each type. If it's kinetic, there's no subtype, it's just kinetic. But if it's potential, it could be electrical, chemical, elastic, gravitational, thermal, radiant energy, it could be all kinds of things. They list 3 here on the screen. We only really worry about gravitational and elastic potential for this course. So while they listed chemical, we don't really consider that for this course. So just kind of a nice graphical organizer to see the flow of how things fit together.
And I assume chemical potential energy would apply to things like heat energy?
Well, chemical energy would be like the joules stored in the bonds, so you're thinking like Hess's law from chemistry class. All right, now there is another category of energy where it's the energy that gets lost and there's no formula for it. So they haven't included it here, but I wrote it off to the side. Because I don't want you to forget that while there's no formula for that dissipated energy or thermal energy or internal energy, all of those terms are used sort of interchangeably. We can find it indirectly, right? If we know that beginning there was 100 joules of energy, and at the end it seems like there's only 90, those 10 joules didn't get destroyed, they just got converted into some sort of random internal energy or sound waves or heat of particles now moving faster. So it didn't disappear, it didn't get destroyed, it's just something we can basically solve by intuition or solve by finding what's missing now, because it didn't disappear, it just is no longer usable. All right, so we've talked about all of that, but just kind of a nice, I thought that was a good summary visual. If you're more into lists, this is another way to think about it, and a reminder of all the variety you might see with the different variables. So kinetic energy, College Board, I put College Board's variable first in each list. Kinetic energy, they just use capital K. But you'll see E sub K or KE in a variety of worksheets and websites and textbooks. It's often referred to multiple ways. No matter which variable they use, it's all about the motion of the object. And that's the same that we've already talked about, just giving you a brief review. Gravitational potential, College Board uses U with a subscript G, but you'll also see E subscript G at times. And that is the energy that's stored because of the separation of two objects, how far apart they are and how much mass they have. And so it's mgh, their mass and how much distance is between them. Almost always, one of the two objects is the Earth, and the other object is something else, a marshmallow or a raccoon or a toothbrush or something. Just could be anything. All right, and we're going to find out the distance between them and how much the gravitational force field would accelerate it downward. The third one, elastic potential energy, you might see it as any of those. College Board uses U sub S for spring. The S stands for spring. And I think they're probably doing that just to try to avoid confusion with EL could be elastic, could be electric. And so using S for springs may be a little clearer. And it is the energy stored because the object gets deformed in some way, usually compressed or stretched somehow. So things like bungee cords and rubber balls and springs, since we call it spring. But it doesn't have to be a traditional spring, it just could be anything that's springy, anything that's compressible or stretchable. Now I put an asterisk in front of each of these because those are the 3 that we focus on calculating, and we have an equation for each. Right? They all have a specific way we can determine their values mathematically. And then the last one again, that dissipated thermal energy, internal energy, whatever you want to call it, whatever version of its name you want to use, you could see a wide variety of variables for that one. They usually just refer to it as a phrase though, College Board, as opposed to a variable. And I think in part because there isn't an equation. So you see there's no asterisk in front of this one because there is no set equation for it. You basically have to figure out, if you know what everything else adds up to, and it looks like some energy was lost, well, it's this. It's the energy that got converted into some random sort of unusable form of energy, usually heat or sound waves. All right, questions about any of that review? Yeah, Griffin.
if there's a question where like, you're like transferring energy, do we assume that like the dissipated energy would be like negligible, or would we have to consider that?
It kind of depends on the context of the question, but it's clear in the way they word it. So if they say things like ignore air resistance and friction, that's code for there's no dissipated energy. If they say there is friction between the surfaces, then they're giving you a code, oh, there's going to be dissipated energy because there's going to be heat whenever there's friction. So it's in the context of the question. So they won't necessarily want you to assume, they'll give you enough context so you kind of know.
Okay.
But they don't come out and just say it directly either, so you have to kind of read into it a little bit.
Like, does an isolated system have dissipated energy?
It depends on how you isolate it, which is what we're going to talk about today. So yeah, we'll see. We define the system based on what we want to be included and what we don't. So that's a good question. That's going to actually be answered in just a few minutes. All right, so let's practice with some pie charts. While you don't generally have to draw pie charts on College Board, I think they're really good practicing just thinking through the transformations. So here we've got a ball being held above the ground at rest. So that's high position point A, and then it's dropped and it falls straight down. Let's just put this down here in the corner. And then when it's at the bottom position C, the ball is just right above the ground. It's like just starting to hit the ground because they're not wanting you to say it's just at rest now. It's like at the bottom of its fall as it makes contact, as it starts to make contact. So what kind of energy would it have at the top?
Potential gravity,
Yeah, gravitational potential. How about in the middle?
kinetic, it's split.
Yeah, it's going to have gravitational potential and kinetic, right? And then how about the very bottom when it's just reaching the ground?
Kinetic.
Just kinetic, right? Because if it's at height 0, there's no more gravitational.
Yeah.
And it hasn't started to like compress or anything. It's just like reaching the ground. So it'd be all kinetic.
It's at like the instant where if you could draw a tangential line, like one molecular point is touching the ground.
Yeah, it's that kind of an idea where it hasn't started to have the chance to compress or slow down yet, but it's basically a molecule's width away. Yeah. All right, so here's how the pie charts could look. All gravitational, then some sort of split between the two, and then all kinetic at the bottom right as it's reaching the ground. Right, and we're assuming here no air resistance because they didn't say in the College Board formula sheet, I've mentioned this a couple times, but down here it says follow these conventions. Assume air resistance is negligible unless otherwise stated. So they didn't say we should consider air resistance, so we ignore it, and there's no dissipated energy in this scenario then. All right. Now we got a baseball thrown up in the air and then it falls back down. Place velocity vectors beside each corresponding baseball. Well, they kind of did that for you already. They put the vectors on there. And then draw an energy storage pie for each lettered position. So what's going to be true at position A?
It's gonna have just kinetic energy.
Yeah, if we're saying that's ground 0, then it's just kinetic energy. If we're saying that's a little bit above the ground, then it's going to have almost all kinetic with maybe a little bit of gravitation. So depends on how we define it. And I want you to know that you can actually define it how you want to solve the problem. So if you're evaluating this as this person throws a ball and it's this high, and then it goes up and comes back down, you might want the ground to be 0. But if they throw it from this high and then they catch it at that same height, you might just want this to be your 0. And you can make it whatever you want. Now, here, they're actually counting ground 0 as the ground. Okay, so it's going to be mostly kinetic with just a little bit of gravitational. And that's how they're interpreting it. How about B? What's going on there?
We know there's gonna be a split between potential gravity, or gravity potential energy
Uh-huh.
and kinetic energy. However, I think it's important to note that I believe it's kinetic energy should be less than the potential gravitational energy because the ball is slowing down.
Mm-hmm. And at this point, it's pretty slow because it's almost to the peak. Yeah, so that's a great conclusion. All right, so let's keep trudging through this here. So Brendan, what do you think about part C? What kind of energy are we looking at there at part C?
Wouldn't that just be potential entirely?
And which kind?
Uh,
Which kind of potential? Gravity or elastic?
It should just be gravity.
Gravity, good. And then Jackie, how about here at D?
It's like both gravity and kinetic.
Good, gravity and kinetic. And then if we compare these two, which has more kinetic? Which one's moving faster?
D.
D, yeah, so this would have more kinetic. And then also this is higher, so it's got more gravitational, and this is lower, so less gravitational. So you could also think it through that way to try to estimate your proportions. And then Michelle, how about this one down here? What are we gonna have here at E?
Is it kinetic?
Uh-huh. And if you're saying that's ground zero, it's only kinetic. If you're saying this is ground zero, then it's gonna be kinetic with a little gravitation, yeah. So you could decide depending on your context. They chose to say there's a little bit of height, so they got a small little bit of gravitational. And then, like Alex said, mostly gravitational with a little bit of kinetic. And then Brendan said all gravitational there at the top. And then Jackie said, yeah, it's going to be split with more kinetic now. And then Michelle talked to us here. We got the end with mostly kinetic, assuming there's just a little bit of space before it hits the ground. All right? Making sense?
Mm-hmm.
So far, we've ignored any kind of dissipated energy though, right? We're saying, well, there's no air resistance, there's nothing lost. So now let's look at one where, oh, not yet. Let's do another one that's before we do anything. So still we're gonna ignore air resistance here. So here, I don't know what this is, like some sort of potato launcher. I can't tell what that is, but we've got some weird thing on a spring that's compressed. And so the dot beside it just means it's like a motion map, no motion. And then it's in the air with still velocity upward. And then it's in the air motionless, like it's reached the peak at the top of its flight. All right, so Aaron, how about the bottom? What's the first picture on the left gonna be?
I think it's all like elastic potential.
Yeah, and specifically since they've said down here below, assuming the resting position on the spring implies that's our kind of zero level, we could ignore that. Like, if they didn't say that, you could maybe say, well, there's some gravitational and some elastic, but if this is our zero, it's just elastic. And we don't probably care that it's a little bit above the ground. So like the gravitational, we would just say, it makes more sense. Let's just make this our zero. All right, Gilbert, how about the middle picture?
Like kinetic,
All kinetic?
like some potential, but like the it is going pretty fast.
Okay, it's going pretty fast, so quite a bit of kinetic. The potential, what kind?
Gravitational.
Gravitational. And then Ashley, how about the top? What do you think about that top one?
Just probably gravitational.
Yeah, it's not moving anymore, so just gravitational. So something like this. Your proportions might be slightly different on the middle one, but it's going to have a mix of kinetic and gravitational there. All right, questions? We good on that one? All right, now let's get to one where we got some dissipated energy. We know here it says across the bottom, some of the energy is converted to thermal on each bounce. So the ball's bounce height keeps getting reduced. That's real, right? That's what really happens. The ball falls, and when it hits the ground, it vibrates the ground. We hear the sound. It's going to warm up the molecules just a little bit. So there's going to be some lost energy to those internal random movements. So, Jesse, how about position A? What kind of energy is going to have there?
Just gravitation.
Good, gravitational potential. And then let's see, Quinn, how about at position B? What do you think?
Elastic potential.
Okay, it's gonna have elastic potential energy. And if we're assuming it's kind of fully compressed, then it's motionless, so no kinetic. And would there be any dissipated at this point? What do you think?
Yes.
Yeah, it doesn't bounce back as high, so that's where it would be dissipated most likely, because they don't say anything about considering the air. So we're still kind of ignoring air resistance, but they are giving us a hint that when it hits the ground, something's happening. There's some vibrations given away there. So in B, we're going to have some dissipated energy with that elastic as it compresses. Tyler, what do you think about C?
Would this be more gravitational? Potential gravitational?
Yeah, it's going to be gravitational, but if we think about the pi as like 100 joules, just to make it like 100%. So if it's 100 joules at A, that gravitational potential at C has to be less, right? but we can't make the pie smaller. It still has to be 100%. So what's the less? The dissipated. So whatever was dissipated at B when it hit the ground, it's still gone. It's like that piece of pie got eaten. So it's still gone at position C. So if we look at A, B, and C, it's all gravitational, and then it's squeezing down and storing some elastic energy as it's losing some dissipated energy because of the vibrations of it hitting the ground and that stuff. And then it flies back up to a lesser height because that energy that was lost to the surroundings is not part of the ball anymore. It's in the surroundings. So the ball can't go as high. So if this is 100, this has to be less than 100. It doesn't go as high, right? And so that piece of pie that got eaten is still gone. And if we compare these two pies, if those two are the same, that's proof that we're ignoring what? If this pi and this pi are the same, what are we ignoring? Air resistance. If there was air resistance, which we normally ignore, but if there was, what would have to be true here? Yeah, this pi would be a little bit bigger. A little bit more would have been eaten away if we were considering air resistance. Yes?
Would there be some dissipated energy in like the stretching of the ball, like, cause I guess it's probably negligible, cause like it doesn't really heat up that much.
Yeah, the heat up probably would be more at that instant down at the bottom, but you're talking about microseconds or milliseconds or whatever, so yeah, you could say that during that very rapid transformation there would be some energy loss, but I think they're just saying it all happened down there when it was colliding.
Okay.
Yeah. All right, how about D? Josh, what do you think about D?
Elastic potential with dissipated.
Good, we got, and would the dissipated be bigger or smaller than the previous pi?
Bigger.
Bigger, yeah, hit again, more loss, so now we got a bigger piece of the pie. And then in the final picture, it's back up to a height again, so gravitational, but all the energy it lost on that second bounce is still gone, and so that dissipated has to still be that size.
Would the amount of energy lost, like at B and D, like have like some sort of difference because of the like height of the apex?
Oh, in terms of like this piece of pie might be slightly smaller than this piece of pie?
Yeah.
Yeah, that'd be logical. All right, so while we're looking at this example, let's show a quick demonstration here. All right, so have these two little rubber balls. What can you notice about them? Do they feel the same? Do they feel different? Like they different masses, or they feel pretty much the same? What do you think? Okay, one's not heavier than the other or anything noticeably? Okay. So why do they do this?
It's one less,
Are they made of the same material?
Apparently not.
does one have, they have a different spring constant over
Yes. They have a different spring constant. This has a much springier value, right? It's bouncing up. It's we could say it's dissipating less than this, right? And what do you notice about the sound? Listen to this one.
Sounds more like
This one.
plastic.
Louder.
Yeah, you can hear the extra sound that's being dissipated here by its design and by the material, right? It's losing a lot more energy, and so it doesn't bounce up hardly at all. Whereas this one bounces pretty good, and it's quieter. It's losing less energy. So these are called happy and sad rubber balls, but I thought that was funny when I found them in the catalog, that that's what they would call them, but. All right. Back to some quick review. We'll fly through a couple slides here. Kinetic energy, if it's stationary, there's no kinetic energy. If it's moving, there is kinetic energy. The word kineo is Greek that gives us that meaning of motion. We've talked about the equation. We know the units. For energy, it's joules. For mass, it's kilograms. For velocity, it's meters per second. And I'm not going to derive that equation today. If we have time next week, I might squeeze it in somewhere, but we'll skip it for today. I want to keep this moving along okay. Gravitational potential energy, we've derived the equation. We've got some sort of mass that's being moved through a distance because of gravity. And so we've talked about that, and I think you guys are pretty comfortable with that. I want to slow down just a bit to review spring energy because we've covered it, a couple times now, but it's been a while. So if you think about a spring, if I pull with 5 newtons of force, that spring is going to stretch a certain distance. If I pull with 4, does it stretch more or less? Less. If I pull with 10, more. So the amount of stretch is variable with the force. If I put more force, it's more stretch. Less force, less stretch. And so we call it a variable force. Air resistance is another example. If it goes through a small amount of air, it's less resistance, less dissipated energy. If it goes through a longer stretch of air, more dissipated energy. So it's variable. Therefore, the work is also variable. Now, when you read questions about springs, they'll often use the phrase an ideal spring or a spring behaving ideally. So they're not talking about whether it's happy or sad or naughty or nice. They're just saying that it's within its limits. So I think some of you discovered when you did that lab back in January, if you stretch the spring too far, it doesn't go back to its normal shape anymore. You actually exceed its limits. And so this Hooke's law linear relationship breaks down because the spring gets damaged, right? So when they say ideal, that's what they're talking about. And we derived in that lab that Hooke's law was force on the y, displacement on the x, and the slope became the spring constant. That's how we kind of broke down the data in that experiment. And Hooke's law, this equation is on the formula sheet from College Board. They just take the negative away. Remember, the negative is just telling us that it's a restorative force. If I stretch it, it's pulling back to unstretch. If I compress it, it's pushing back to decompress. Okay, so it's always restorative in nature. Some books add the negative, College Board just drops it. All right, now let's talk about the energy. And when we did the whiteboards, I challenged you to think about what might the area under the curve represent. And a few of you did some researching or relied on some prior knowledge, and you figured out the area under the curve had something to do with work or energy. And today we actually confirm that. If I take force times distance, what does that give me? What's force times distance? It's a Newton meter or a joule. That's the equation for work, right? Force times distance. So we're kind of proving now with what we know now that we've gained some more information, it is actually the work done on the spring or by the spring. And because of the work energy theorem, that's also the amount of energy stored in the spring when we do that work. So you could consider the area under here as either work or energy. They're focusing on it as the elastic potential energy. And if I want to find the area under the curve, it's a triangle. So it's 1/2 base times height, right? 1/2 x times f. But from Hooke's law on the previous slide, we know that the force of a spring is equal to k times x. So if we substitute kx in for force, we get 1/2 kx times x, which is 1/2 kx squared. So this equation can be derived graphically from the linear relationship that exists in Hooke's law. It's a pretty easy derivation if you understand that it's just the area under the curve. All right, so that's where that bottom equation comes from. It's not sorcery, it's just math and physics. All right, questions? A little bit of review with a few new insights sprinkled in. All right, now this kind of question is extremely common in College Board testing. I don't bet, but if I were betting man, I would put money on this being on the test somewhere, because every year it shows up somewhere. Sometimes it's in a free response question. Often it's in one of those like multiple choice questions where like part A, or sorry, it shows a picture and it says the next 2 questions involve this diagram, and then you have to answer a couple of questions about it. So I want to make sure you understand it. Now, we won't just talk about it today because it's an energy question, it's a momentum question, which is our next unit. It's also a simple harmonic motion question, which is the unit after that. So we're going to revisit it 3 units in a row. But for today, we're focusing on the energy. And what they're saying is, this is a frictionless surface. I always love those magical frictionless surfaces that somehow exist in the lab. So we're stretching this spring out by pulling this box to some distance, and then we let go. And because there's no friction, the spring pulls it back. And when it reaches this midpoint, it's got momentum and inertia, so it just keeps going. And then it squeezes the spring down some distance. And then it reaches the limit and it pushes it back. And it just keeps bouncing back and forth, oscillating back and forth, because there's no friction to slow it down. Okay? So if I'm holding it here, what kind of energy am I storing in it? Elastic potential. When I let go, that elastic potential begins to convert to kinetic. What can we say about the kinetic energy right here where the spring is no longer pulling it or pushing it? What's that? Purely kinetic. Out here the spring is stretched. Down here the spring is compressed. But right here the spring is relaxed. In fact, if it wasn't moving, if I just sat the block there, it wouldn't go anywhere, right? Because it's not stretched or compressed. But because I stretched it first and let go, it's not going to stop there. It's going to keep going, right? Because it has momentum. So it's coming along, and here it's going to have maximum velocity, maximum kinetic energy. Over here, what kind of energy does it have? All elastic potential again. Back here, all kinetic again. Down here, all elastic. It's just going back and forth, right? It's converting back and forth. If I picked someplace kind of in between, it would be a split. Like if I picked a spot right here, the spring is still pushing, so there's still some elastic, and it hasn't reached maximum speed yet, but it is moving, so it's going to be some mix of elastic and kinetic in between those two extremes. All right, so again, they might ask you a force question, which we'll address when we get to momentum. They might ask you a momentum question, which we'll also address then. They might ask you a period frequency question on simple harmonic motion, which we'll talk about 2 units from now. So we'll keep revisiting this, but this is a super common type of question. Any questions from you about the energy relationship here? That's where we're starting this today. That making sense? All right. Now we get to LOL graphs. So you look at without the like dashed lines, it looks like LOL a little bit. And so some students and teachers call it that. I doubt if you'll laugh much while you're making them, but it's what they look like. So you have a hand, what's that?
Isn't this done in chemistry a lot?
Yeah, you probably, if you've had chemistry, you probably have done these before. So what we're doing is on the left, we're going to analyze what is all the energy that it has in the beginning. And then in the circle, we're going to put, well, what are the things we're including in the system? And then on the right side, we're saying, well, what is all the energy distribution after? And it's always going to be a point A to point B, like 2 different points in time. And then from that, we generate an equation. So if you've had chemistry, you've done this before. If you haven't, we'll bring you along easily. All right, so here's a scenario. And I gave you that, remember the spring chicken handout that I gave you with the pictures of the spring? On the back of that's a bunch of bar graphs. So if you want to use that, you can. If you picked up worksheet 2 from the back table, you might notice on the back of the first page, you're going to see some of this as well. So you could also just kind of be doing worksheet 2 as we go. If you're watching the video, worksheet 2 is in unit 4. Different units in different classes. AP 1, unit 4. So if you're finding this worksheet on Access, you can find it there. You what? Yeah. All right, so I don't know if these are exactly in the same order on the worksheet, but I think they're all covered. So they might be in the same order, I forget. So we've got, in the situation shown below, we've got a spring launching a roller coaster cart from rest on a track into a vertical loop. Assume the system consists of the cart, the earth, the track, and the spring. So the circle in the middle where it says system flow, that is where you just describe the items that are in it. So they've said in that circle we should write cart. We need the cart because the cart's what's moving. So that's the only thing that can have kinetic energy. They said also include the earth. We need the earth because that's what creates the gravitational field. So that's what gives us gravitational potential energy. Then they said include the track. We need the track because that could create friction possibly, which would give us the dissipated energy. And then they said include the spring. We need the spring because that's what gets compressed or stretched and makes the elastic potential energy. So if we want to represent all 4 energy types, we need all 4 of those items in our system. So we just write those 4 words in the circle. Now it says, you may neglect the effects of friction and drag. So we're ignoring air resistance like College Board normally tells us to, but we're also ignoring friction here, okay? Just for now. We'll come back and consider it in a minute, but for now we're ignoring it. So what kind of energy does it have at position A? Elastic. All stored in that compressed spring. What kind of energy does it have at B?
Yeah, kinetic.
Yeah, it's got kinetic because it's moving, and gravitational potential because it's now above at a higher height, right? And they always draw these little trails behind it to show if it's still moving. So if you don't see those trails, it usually means it's come to rest. But there it's clearly moving through the loop still.
That's not a position to rest.
Yeah, you wouldn't, if you're on a roller coaster, you don't want to stop there. All right, so here is what it would look like if you're following along in your worksheet or in your notes or wherever you're putting it. We start with a bunch of elastic energy. Now they've just filled it all the way up to 5 bars of energy. That's arbitrary. We could have picked any number, but they've just chosen that value. You can see in the circle they wrote cart, track, spring, and earth, just like the question said they should. And then at the top of that loop, they've said it has mostly gravitational and some kinetic. Now, why did they pick 4 and 1? I have no idea. I probably would have picked 3 and 2, or you could even pick 3 and 2 the other way. We don't really know. There's no quantitative information. But we know that it has to have some kinetic because it's moving, and some gravitational because it's now at some height above the ground, and that however much this is, it has to add up to that. Because we didn't lose any to friction, we didn't lose any to the air resistance. So if I made 5 bars of elastic over there, I need 4 plus 1 over here to make 5 on the right. And from that, we can generate an equation. The elastic energy is equal to the sum of the kinetic and the gravitational. All right, so the power of this is really in the equations that we can derive. The College Board, while they don't generally ask you to draw pie charts, they do sometimes ask you to either draw or interpret bar graphs. So you do need to be more comfortable and confident with this process. More often, the equation is what we're trying to get. And once we know that that elastic is converting into kinetic and gravitational, now we can put, instead of elastic, 1/2 kx squared, instead of kinetic, 1/2 mv squared, instead of gravitational, mgh. And we can substitute those in and find out how high is that, or how much was the spring compressed, or what's the spring constant. We can find out any of those things based on what was given. So that's where the value of the equation comes from. That's going to be the focus of Tuesday's or Wednesday's lesson next week for you guys. Questions? Is it making sense so far? All right, so the next scenario, and again, I don't remember if it's the second one on the worksheet or if they're in the same order or not, might be. But the next one says, repeat part A, but we're just including the cart, the earth, and the track. The spring is not included. So we don't put the spring in that middle circle. So the cart is included, so we can use kinetic energy. The earth is included, so we can include gravitational. The track is included, so if there was friction, we could consider dissipated, but it says we're still neglecting that stuff. But the spring is not included, so what can we not use?
Elastic energy.
Yeah, we cannot use elastic energy. So if we can't use energy, what's the other option? Any ideas?
Apply force.
We could think about the force,
Work.
and the force times the distance would give us the work. So we could say, oh, if the spring's outside of the system, it just does work on the system. Right? So it would look like this. The spring is not in the circle, so we draw an arrow going in saying, oh, the spring is actually adding work into this system, doing work on this system.
That's thinking a little outside the circle.
Nice.
Are we gonna expect it to do something like that on the AP exam?
Possibly.
Okay.
I'll let you process it for a few seconds, and I'm going to tell you why, and probably how it would relate to an exam question. So in our notes a couple days ago, we said there's this thing, this work energy theorem, where the change in energy is equal to the work done, or the work done causes a change in energy, however you want to think about it. So we can substitute work in if something's not in the system, but it seems kind of arbitrary, right? Like, why did they pick spring? Why didn't we just put in the system? Well, what if you don't know the spring constant? Then this equation becomes less beneficial. But what if you do know how much force you applied to the spring? Now you can use this instead of this. So pulling the spring out of the system is really just a strategic choice mathematically, right? You're just saying, well, I don't know this, but I can find that. So let's just say the spring's not in the system and let's use work instead of elastic energy. And then it gives you another mathematical option to solve the problem a different way. Yeah, Griffin.
So if you're figuring out the work the spring did, that would be the force, and then would the distance be the distance the object travels, or the distance the spring like stretches?
The distance the spring pushed the object.
Okay.
So it would end up being most likely just the way the spring stretched or compressed, depending on the scenario. Yeah. So if it said the spring applied a force of 15 newtons over a, half of a meter distance, then we would know how much work was done by the spring on the cart. And then that's how much energy gets imparted to the cart. And so right when it leaves the spring, it'd all be kinetic. But by the time it reaches this part of the loop, some of that kinetic energy has been lost because it's now higher, it had to go uphill, and it's turned some of that kinetic energy into gravitational potential. All right, any questions beyond that for this scenario? Here they took the spring out, so we have work going into the circle. If they had friction, they could take the track out, and then we could have like an arrow coming out of the circle to show it leaving. So if you're taking away something that would normally be represented here, you can just use it as work going in. If you're taking away something that would be normally represented on the after, then you just show it as an arrow leaving the circle. Okay, so you could do work either way, work going in or work coming out. All right, so you could find, because is there an equation for dissipated energy? No. So maybe you don't want the track in there and you just want to show the work coming out and then find the work done by friction or something. So there's a lot of different ways to approach it. There's not one way, but you can have work going in if it's at the beginning or work coming out if it's at the end. All right, next scenario. Repeat part A. We're putting everything back in the circle again. So string, track, earth, spring, track, earth, cart, everything's back in the circle. But now it says there is friction. So they don't say anything about drag, so we should still ignore that, but there is friction. So what energy do we have at the beginning?
Spring.
All elastic, spring energy. What do we have at the end?
We're gonna have kinetic, gravitational, and dissipated.
Yes, kinetic, gravitational, and dissipated. Now, we can't have more. If we started with 5 bars in the beginning, we can only have 5 bars at the end, right? We can't add energy. So where do we take it from? Do we take it from the gravitational or do we take it from the kinetic?
Probably gravitational.
Did you say kinetic? No? I thought I heard you say that.
Yeah. You know what, I'm just gonna say.
Quinn, give us some rationale.
Because gravitational is height times mass times g,
Uh-huh.
and the height's the same, g's the same, the mass is the same.
Uh-huh.
But the velocity for kinetic has to be slower because the friction is also against the velocity.
Good. Yeah, perfect. So we have to be careful about what we take it from. It wouldn't, in this scenario, take anything away from the height because it still goes to that same spot in the loop. But it would slow the track down, or slow the cart down, I mean. So just like Alex said, we got our elastic energy equal to kinetic plus gravitational plus dissipated. And just like Quinn clarified, the kinetic would be diminished to be replaced in part by the dissipated. Still has to add up to the same total as it started with. Any questions about that scenario before we look at the last one? Are they in the same order or are they in a different order on the worksheet?
Same order.
It's same order too? Okay, so you know what's coming next. All right, last one. Same system as part A, so cart, track, earth. What am I missing? Spring. We got all four in the circle again. Except now the cart is lower. It's just still going up the side of the loop. And we want to scale it consistently like we've been doing before. We want to make sure we're kind of using the same sort of thinking. And we're back to ignoring friction and drag again now. Okay, so they're just kind of waffling you back and forth, thinking about different things at a time. So what is it at A?
5 bars of elastic.
All elastic. And then at B?
You're probably gonna see a reduction in well, either you're gonna see an increase in gravitational because it's gonna be great enough to where the cart won't. Well, then again, I'm thinking in terms of gravitational force, right? Because if you're gonna have a higher gravitational force, the cart may not necessarily make it all the way up. However, if you have a lower gravitational energy, maybe somehow that's gonna prevent it from going in the full loop.
So gravitational potential energy is based on the mass of the cart, which would be the same. Gravity, which would be the same. Acceleration due to gravity. And the height,
It's gonna be lower.
which is lower.
So we're gonna have a lower gravitational energy.
Yep. And the total can't change though. So if that got lower,
Will we have a higher dissipated energy?
Oh,
Would
that's-
that become
No,
high
it's-
dissipated energy?
yeah, higher kinetic, right? Because they're saying we're not doing dissipated here again. We're keeping friction and drag out of it.
Mhm.
So it just means it's going to be moving faster, basically, right? More kinetic energy, less gravitational. Now they've said 3 kinetic, 2 gravitational. Who knows? Maybe it's 2, 3 the other way. We can't really know for sure. They didn't give us enough detail to really truly make it purely quantitative. But we know compared to before, there should be more kinetic because they wouldn't have slowed down as much, right? As it goes up, it's going to keep slowing down. So it wouldn't have slowed down as much. So it's going to have more kinetic energy. And it hasn't gone as high, so it has less gravitational. All right, so we good with worksheet 2? Is it making sense how to fit these pieces together in these puzzles? All right, so your assignment is to finish the first page. You should have the whole back of it done if you were following along as we went. So I just want you to do the front of it. We're not supposed to give big assignments due on Mondays, so that's a pretty brief one. Just finish the front of that first page. For the rest of today, I want to give you some time to do your test corrections. All right, so we've got what? We get out at 20 after?
Yeah.
Okay, so we got about 10 minutes, so it'll just be a start. But on Monday, I'm going to give you quite a bit of that period Monday to continue test corrections. So get a quick look at it today, maybe start working on it. Monday, you'll have a bigger chunk of time. As you work on it, remember your corrections need to be on a separate sheet of paper. So I'll pass them out, and you can start getting at it.
No.
Chris changed glasses. I think so. I mean, he's not here.
Yeah, his math class changed, and so he had to switch sections. So now
What section is he in?
he's in section 3 now.
Is that the one before us?
Normally, today is after.
Oh,
Yeah.
And these are just in alphabetical order because it's easier for me to enter them that way. Except I think yours might be last because you migrated yours.
This one?
Yeah,
Way better than
today assembly is in the gym again.
That sounded actually a lot better than I thought.
I don't know what it is.
This is a rough one.
Oh, I got nothing wrong. Dude, I swear, look at my list.
I don't wanna see my Afro-Cues. I don't wanna see my Afro-Cues.
Oh, shit.
Into the alphabet.
I would so many of the multiple choice. I got -4 total on my multiple choice.
It's
Funny that I got -8.
No, but what, first test I do.
Alright,
Oh,
Mr.
I'm still the last one.
Hey,
That's good though.
got plenty, right? Okay.
Alright. Oh, a lot better. To be honest, I don't even do that bad on this FRQ.
Again, don't forget if you're doing corrections, if you're gonna go ahead and start them in these few minutes, make sure you're putting them on a separate sheet of paper.
Did you do good on any of the FRQs?
I did pretty good on this one.
Did I see that one? Yeah, I got that one, I got that part one too.
Because it says feels 4 times heavier, so I put 2,400 on.
That's what I did. That's what I would.
Yeah, we got the same answer.
I also.
Oh, you did better than, no,
We got 19.
I'm glad about this one, ish. This one.
What?
Did you get this one?
I think this was. Minus
Oh, yeah.
Oh,
I
yeah.
wrote why the mass doesn't change, but I forgot to write, oh yeah, by the way, the mass happens when the same mass.
I thought it was yeah. It was I divided by 400 and.
Ooh.
Oh, because do you remember?
No, it's the
That's your jaw feeling.
Oh, it's so much better.
Oh, yeah.
Because that makes
When I did
sense.
the concert Tuesday,
That's what I did that bad.
like about like 2/3 of the way through, like it started
Okay.
pretty bad. Yeah, now I'm at the point where I can do just remotely, like the full area of my jaw.
Yeah, it has to be
That
so
was
careful.
the latest.
A little careful, and I have to always rinse my mouth out with water or mouthwash just to make sure I find
Yeah.
What do you put in
Yeah.
the
Did they give you like a water pick or anything to help?
No, but I do have one at home.
Yeah.
But I mean, really, all I've been doing is just switching with mouthwash.
Mr.
I mean, it
Webb?
also has
Yeah.
antiseptic. So.
I think both got this exact same thing wrong and we're really confused.
Alright. Yeah, we're looking at.
It was the last
The
one.
last one, okay.
What else did you?
I heard 500 word essay for Bible.
So this would be the fourth of
Online Bible,
the
it's ridiculous.
calculate small g.
Literally, in-person Bible won't fit
It's
in my.
this relationship is saying, you can find the weight of something, m times g, and you can find the weight of something.
They basically can't show that you do anything besides the assignment. You have to turn it in. So they make you do like a ton of assignments that just
Are
like.
squared. So if you just wanted to find g for
Oh, you
planet,
take out the ab.
that cancels out.
Oh, okay.
So you're, to find little g is just big G times the mass of the planet times the radius.
Oh,
I
okay.
scroll
I have 2.1 in there.
No.
Mr. Webb,
Yeah.
what's high school head of schools list?
High school.
It said I got an award, but I don't know.
Head
what
of
it is.
schools list is a 4.0 and higher.
Oh.
Oh, yeah, I have no idea.
Big brain.
Also, I have another quick
So
question.
just wait till.
So for,
Okay.
That's easy.
oh,
Yeah,
is
easy.
it
We did
503
4.0.
times
wait
4,
till
not 600 times 4?
It should be the normal four
I
times
should
four.
do the college reading.
So it'd be this, yeah.
Yeah.
Gilbert.
Do you have that?
Two
I don't
different.
know, I don't have it.
What are you doing?
Maybe you can.
Should I put that under awards?
Under awareness.
Yeah.
I have the resume.
It's eight multiple choice.
I'm kinda sure.
Yeah, it's the same thing.
What's your GPA?
And then they
I
have like.
wouldn't have a worse score than you if I got all my multiple choice right.
Like
Because I'm
head of
taking
school and
jazz
like principal or whatever.
Yeah. 'cause I'm doing that.
Yeah, you should put that on.
This one doesn't make sense.
And by the way.
The other day, like, you like
Okay.
this,
Yeah.
and then,
No.
do you see that?
What, which one did you put?
Oh, it makes them, well, I did this.
Yeah,
'cause
no,
I
because
thought-
velocity is always pointing away from, like, it's like always pointing where it's traveling like away.
Okay, I was thinking it's accelerating, and then if it were to let go, it would just go straight, so.
No, it's accelerating
Should I
downwards.
have that?
Velocity is always like transverse, it's always the straight, like tangent
Okay.
line.
That's for freshman year.
What was the
Like,
I-
So did you cut the straight, that's